This lecture is entitled Generating Knowledge and is our second look at magnetism. It says, I do not think there is any thrill that can go through the human heart like that felt by the inventor as he sees some creation of the brain unfolding to success. Such emotions make a man forget food, sleep, friends, love, everything. And that's a famous quote by Nikola Tesla, and he was one of the most famous inventions. He's kind of taken a backseat to Edison, but he was a brilliant man who we'll explore a little bit of what he talked about in this unit. The first thing is we want to know what we should learn. You should be able to tell the differences and similarities between a motor and a generator, and also see what a transformer is and why it's useful to our everyday life. And then we should also be able to look at a transformer and ask ourselves whether or not it violates the law of conservation of energy. So what we already know that magnetic fields apply to forces and or things that are moving in them, and that magnetic fields apply to forces. So there's a relationship between the force that moves through a magnetic field and the magnetic field causing a force. And we actually see that with levitation. There's a magnetic difference between these two that causes a force. And sometimes you can have a force that can actually cause a magnetic field, like you do whenever you have a moving charge that goes through a wire. So here's what we learned. We learned that electric and magnetic fields are linked. You saw this simulation right here. We saw that as you move this magnetic field, it actually influenced the electric field here, causing the light to go bright and go dim, go bright and go dim. We also saw that moving electrons are actually magnets. And we saw that a moving magnetic field can actually create an electric field. That's actually a very useful thing. In fact, what we're looking at now is actually called electromagnetism, or E&M. Now, the first thing that we need to do is we look at a generator. Now, a generator became the basis of kind of our civilization as we know it. Basically, it's the idea that whenever you have a magnetic field, you can actually take magnetic or you can take mechanical work and you can convert it into electrical energy. Now, the key to this particular thing is the idea that you're converting energy. So I've got mechanical work, which is energy, and I want to convert it to electrical energy. But you can't just rub your hands together and have them create electricity. Instead, what you have to have is you have to have an intermediary. We have to rely on the properties of magnets and electrons. So although you are doing a crank and you're actually applying a force and it's moving, it's the fact that you are actually causing the crank to rotate a magnet, which actually allows you to create an electrical field. Now, a generator is how we create almost every version of electricity that we have today. Now, you generally only hear about generators whenever the electricity goes out and you have some sort of backup generator. It's just that the generators that we have are very far away and very large scale, but they're the same basic thing. Examples of common generators. Okay, you're actually using a generator whenever you start your lawnmower. Okay, you're actually applying a physical work to move a magnet, and that magnet creates an electric current, and that electric current actually ignites the gasoline and starts the engine. So that's another example of a common generator. You using physical work by pulling the string to rotate magnets to cause a spark to ignite the engine. Okay, almost all forms of energy use this. An example of that is a hydroelectric dam. Now, a hydroelectric dam, you're not actually pulling a ripcord or cranking a magnet. Instead, what it does is it uses water. You have water that comes through here, and there's a gravitational potential energy that the water gains as it comes through this intake. And what it does is it actually causes a turbine to turn right here. And that's the key step. When the turbine turns, it causes a magnet to rotate, and that rotating magnet is a generator. And then the generator can pump out electricity to long distance power lines. So it's just not, we're not doing the physical work this time, we're not cranking it, we're using the idea of the water's gravitational potential energy to make this occur. Now, different power plants are going to operate in different ways, but this is a pretty common approach, the fact that you are using the moving water to rotate a magnet. Now, a coal-fired power plant is a little bit different in the sense that there is no water that's actually making it move. Instead, what you do is you have some sort of water source. It's a river, a lake, they usually have a reservoir at some point, and that water is actually pumped into the plant itself. And then what happens is you get it to this holding tank, and then you have a furnace. And this is where you burn the coal. When you burn the coal, it releases a large amount of energy, and that energy actually causes the water to turn into steam. That steam then rises, and as the steam rises, it causes a turbine to turn. Once again, it's a magnet that turns, and whenever you rotate a magnet, what you do is you create an electric potential. And that electric potential is then pumped out along a transmission line, and then you have electricity. Okay? A nuclear power plant operates the exact same way, except instead of burning something like coal or natural gas or something along those lines, you have an alternative source of heat. The nuclear reactor is the source of heat. So you have the same basic idea that you're pumping in water, and then you have this right here, which is called the steam generator. The steam generator is just what happens when you pump the water through the reactor. And the reactor is where you have a nuclear reaction going on. Now we'll explore that in a little bit more detail in the next unit, but basically the idea is that you have heat generated by a nuclear reaction. It's a great deal of heat for a small amount of fuel. And in doing so, you've converted a lot of water to steam. That steam rises, causes a turbine to turn as it depresses. So you've got super hot steam, but as the steam condenses, it falls, causes the turbine to turn, and then that water is recycled through this process. Some of the properties that we have for generators are very similar to what we talked about before. Generator properties are affected by the number of coils in the wire. The more coils that you have in a generator, the greater difference or potential that you're going to make. How fast the magnet moves through the wire. So if you can take the magnet and you can rotate that magnet extremely fast because you have very high power steam, then that's going to create a greater potential. The strength of the magnet itself. If you are rotating a very weak magnet, you shouldn't expect much. But if you have a very, very strong magnet rotating, you can expect a great change in electric potential. And then finally, what you have is the cross-sectional area of the loops. So you're creating this large loop in which the electricity, or this thing that rotates. The larger the surface area of this particular thing, the more it's going to create as far as an electric potential. So what is a crank radio and what is its applications? And you see one right here. This is a crank radio. What you do is you pull this thing out right here and you rotate that crank around, and as you rotate that crank around, you will start to hear a signal. Now, radios are generally very low power devices. Okay, you can operate a radio on a regular battery for quite a long time. But in an emergency situation or something in which you have dead batteries, a crank radio actually works very well. You can generally turn this crank and you can operate the radio for up to 10 to 15 minutes depending on how long you crank it. And when it runs out, you just crank it again. And the reason for that is this crank is actually attached to a magnet. And then whenever you have that magnet, it's rotating. That rotating magnet creates an electrical potential, and that electric potential will actually power the radio. Next, we have the idea of a transformer. And what a transformer is, it's a way for us to change the voltage that we have between two different circumstances. So it allows us to step up or step down the voltage depending on what we're trying to do. Now, the idea of a transformer and the ability to change the voltage from one thing to another is really the idea, that's the basic idea behind why we have an alternating current system. Now, we talked about the alternating current and the direct current system earlier when we talked about electric circuits. Now, the reason why we have this is the ability of alternating current to change voltage. Now, it is not secretly an alien robot in disguise. You can imagine you'll probably see that on your test. So now, why transform? Okay. If you did not have the ability to transform, power plants would be a lot closer to your house than you'd probably be comfortable with. Okay, being able to change the voltage to a very high level allows you to transport voltage over long distances. Okay, the higher the voltage, the easier it is to transport electricity across long distances. And because of that, you can put a power plant far away, and then you can use it to bring power to remote locations. But then the ability of a transformer to step down the voltage allows us to use it in such a way that it's not dangerous. It's not like you're going to plug your iPhone charger into the wall and it's going to explode. So we can actually change the voltage, And this is what's called an alternating current. And whenever you change the voltage, an example of this that you actually have is whenever you look at, well, we'll look at that a little bit later. It says whenever you do this, you can actually have what's called a primary coil and a secondary coil. So the primary coil is generally where your supply is. So let's say that my primary coil that I have to begin with, the primary coil that I have to begin with is, let's say, I don't know, like 100 volts. 100 volts isn't very much. Let's say that I want to step up this voltage so that I go to the next, so I can transport it over a long distance. All I have to do then is have a small number of loops on this side of the coil, and then I actually connect it to what's called a secondary coil. And then what I do is I increase the number of loops. And when I have an increased number of loops, I'm actually stepping up the voltage. Okay, this is an example that these things cannot touch. Okay, if you have these things touch, you're going to have electricity go between the two in such a way that you don't really want. You want to bring them close to each other so that the motions will induce each other. The magnet of this one, by the wire wrapped around this one, induces the same magnet on this one, equal and opposite. And at that point, because it has more coils that it's divided up amongst, is the reason why you have a different voltage. There is no difference in energy between these two. Remember that what you had for voltage is the amount of energy that something has per charge. Okay? What we have here by having a greater sense of wire is you've increased this particular value right here. So whenever you change the amount of charge that's present, the energy can stay the same and you can manipulate the voltage up and down. A motor is very, very similar to a generator. In fact, it's just the opposite. Okay, where a generator, you use some sort of physical work to rotate a magnet and then create electricity. A motor works in the exact opposite. It takes the electricity and causes it to do physical, and uses a magnet to cause something to do physical work. So it's basically the exact opposite. One turns electricity into work and the other one turns work into electricity. So as this thing rotates, which coils north and south and which south gets changed, it reaches an end, it kind of rotates through. So it gets to the point where it's attracted to this and then it misses it and keeps going. And so that's kind of a basic explanation as for what a motor is. Motors are the opposite of generators. They convert electrical energy into mechanical energy. And so what you see here is this is a motor for a vacuum cleaner. You can clearly see the coils of wires that are going around. And that's an example of how you can actually take something and cause it to do physical work. The last thing that we really need to explore in this presentation is the idea of the right-hand rule. The right-hand rule is a shortcut that allows you to kind of predict the direction of a magnetic force or a magnetic field for a current. There are pretty much two right-hand rules. This one that's shown right here is actually right-hand rule number 2. And it basically says that whenever you have an electric current that's moving in a wire, you take your thumb and you point it in the direction that the current is moving. And then you wrap your fingers in a half circle, and that is the direction that the magnetic field points. If you notice when you do that, your fingers are going to form a circle around the wire because it is a circular magnetic field. So that circular magnetic field that goes around the wire is very strong immediately around the wire, and it actually gets big. It gets less and less strong as you increase your distance from the wire. That's right-hand rule number 2. Right-hand rule number 1 relates the idea of magnetic field, force, and current. So basically what you do is you take your thumb and you point it in the direction of the current. If you notice, that is the exact same thing that we did here. Your thumb is always going to be the direction of the current. And then what you do is you point your index finger in the direction of the magnetic field. That then allows your palm, or you can stick your middle finger towards that direction. I actually like to use my palm in that direction. That actually shows you the direction of the force. What you see here is that the current, the magnetic field, and the force are always perpendicular to one another. This is at a right angle to this, which is at a right angle to this and this. So they are all orthogonal, perpendicular, at right angles, 90 degrees. All of those things describe what is the relationship between these. So if we take a look at an example, it says draw the relationship between a motor and a generator. Now, how you're going to draw this is they're basically the same thing. So if you come up with some sort of way to say that a motor is pretty much the same thing as a generator, but for a motor, you have electricity goes to work, or excuse me, yeah, goes to work, and for a generator, you have work going to electricity. They're basically the same idea. However, you can draw that works best for you will work. Now, this one says if an electric current was moving in the direction of the left side of your page of paper. So, for example, you have the electric current that is moving this way in the direction of the field lines. So, you're talking about a magnetic field at this point. Excuse me, yeah, a magnetic field is directed into the paper. When something is directed as into the paper, you represent it with an X. The reason why is you think of it as an arrow, like a bow and arrow. And when the arrow is shot into the piece of paper, all you see are the tail feathers. And so since you see the tail feathers, it makes an X. So you have it going into the page. And then the question that you have is, what is the direction of the magnetic force? So you point your thumb in the direction of the current. You put your index finger in the direction of or into the page, and what you'll find is that your palm or the middle finger will actually be directed towards the bottom of the page. So you would say that the force is directed towards the bottom of the page.